the James Webb Space Telescope is upsetting the apple cart. All of a sudden, we realize that we may have to rewrite all the textbooks about the beginning of the universe. The James Webb Space Telescope, JWST, has just unveiled one of the oldest galaxies ever seen, a revelation so monumental that there's no going back from this. What does this ancient galaxy tell us about the origins of the universe? Join us as we explore this mind-blowing discovery and its implications for our understanding of space and time. Get ready for an awe-inspiring journey to the farthest reaches of the cosmos in this captivating exploration into the intricacies of astrophysics. We will uncover why the universe might be much older, and we will also unveil the audacious predictions made by forward-thinking minds a century ago. Let's look into why scientists have declared they were wrong and why the universe is really 27 billion years old. The inquiry into the age of the universe stands as a cornerstone in cosmology. It is a profound quest to understand how long the universe has expanded since the monumental Big Bang. This explosive event gave rise to everything observable in the cosmos today. Throughout history, the universe's age has been a subject of intense debate, even within the scientific community. However, contemporary consensus among most cosmologists indicates that the universe is approximately 13.8 billion years old, with an uncertainty of less than 1% regarding the duration of its expansion since the Big Bang. Determining this time frame commonly involves two primary methods. The first method involves assessing the universe's expansion rate using the Hubble constant, a metric derived from observing the velocity at which galaxies are receding from us. By estimating this movement, scientists can approximate the time that galaxies took to arrive at their present positions. The second method involves the examination of ancient stars in the universe found in entities like globular clusters. Scientists can ascertain their ages with a high degree of certainty by analyzing factors such as brightness, color, and rotation rate in these ancient stars. By employing these methods, astronomers establish a minimum age for the universe, shedding light on its origins. Both methods provide compelling evidence that the universe is approximately 13.8 billion years old, with a margin of around 21 million years. Moreover, this age estimate aligns with numerous other observations and models regarding the universe's current state. Notably, it fits well with cosmic microwave background radiation data, representing the earliest light signatures we have captured from the universe post-Big Bang. However, despite the unity of results from these cosmological models, specific astronomical observations defy this estimated universe age. Some discoveries stand in contradiction, challenging our current understanding. A significant case in point is the star identified as Methuselah. In a study published in 2013, scientists calculated Methuselah's age to be 14.5 billion years, exceeding the widely accepted age of the universe. Critics of the Big Bang theory frequently emphasize this anomaly as a possible imperfection in our comprehension of cosmic origins. Though Methuselah's existence might seem at odds with the Big Bang theory, critics often neglect a crucial factor: certainty. A more precise calculation places Methuselah's age at 14.45 billion years, with an uncertainty of 0.8 billion years. Over time, these measurements are becoming increasingly precise. However, the current estimate accounts for the moment. Assuming the maximum uncertainty of 0.8 billion years, Methuselah fits within the acknowledged age range of the universe, approximately 13.65 billion years. But if the uncertainty is considered in the opposite direction, the star markedly exceeds our existing estimates, posing a significant challenge to current cosmological models. Another recent complication for astronomers is a discovery made by the James Webb Telescope. It stumbled upon a cluster of galaxies believed to have originated merely about 300 million years post-Big Bang. While this time frame aligns with the current estimated age of the universe, the young age of these galaxies challenges our preconceptions about the formation of galaxies of this magnitude. Conventional wisdom regarding the formation of galaxies suggested their existence at this stage was implausible. They appeared more advanced in development than previously deemed possible within that era of the universe. Remarkably, they endured intense radiation and collisions with other celestial bodies. Consequently, these galaxies earned the moniker the impossible galaxies. The prevailing sentiment from these discoveries suggested a need for cosmologists to re-evaluate their models concerning early galaxy formation, and some questioned the accuracy of the JWST findings. However, what if our current assumptions are incorrect? What if these stars and galaxies are attempting to tell us that our understanding of the universe's age is fundamentally flawed, but we are hesitant to acknowledge it? Rendra Gupta's name was relatively unknown until recently. However, that has changed as Gupta, a professor of theoretical physics and cosmology at the University of Ottawa, is on the brink of making history. He is the only one offering two coherent explanations for the existence of dozens of galaxies deemed impossible at the outer limits of the known universe. Gupta's approach to resolution is straightforward, grounded in two theories that have been known for a century but were not taken seriously at the time. If Gupta's propositions prove accurate, we may need to adjust ourselves to an entirely new number for the age of the universe, 27 billion years, with an uncertainty of approximately 40 million years. Gupta substantiates his claims with compelling evidence. The implications of this discovery would be profound for the scientific community. This is particularly true for those who have long adhered to the Big Bang theory and the prevailing estimate of the universe's age at 13.8 billion years. Should Gupta's study prove accurate and confirm a minimum age of 27 billion years for our universe, the implications would be monumental for our understanding of the cosmos. Numerous existing theories and models would need reassessment, some would prove incorrect, while others might undergo revision and updating. This wouldn't merely translate to an increased workload for scientists. These advancements could also present an opportunity to address long-standing questions and mysteries about the universe's origin that have eluded us until now. For instance, an enduring enigma in cosmology revolves around what existed before the Big Bang. If the Big Bang marked the start of time and space, the question of what preceded it doesn't seem very smart. However, a deeper understanding becomes imperative if the Big Bang was not the absolute beginning but rather a transition between universes or the start of a multitude of universes. Perhaps there was a pre-existing universe before ours, or our universe originated within a much larger structure, something like an ancient multiverse-like entity with parallel universes and galaxies older than our universe. What if there are stars and galaxies scattered across the cosmos that predate the very existence of the universe? The concept might seem paradoxical, and indeed it is. However, these observations are not mere speculative musings but grounded in reality. As mentioned earlier, a solitary star, Methuselah, defied the expected age of 13.8 billion years. Researchers initially grappled with the possibility of a measurement error in an attempt to rationalize this anomaly. Then, in July 2023, the James Webb Space Telescope made startling observations. Dozens of galaxies, seemingly older than expected, emerged in its lens. These galaxies purportedly existed a mere 200 or 300 million years post the presumed Big Bang. Intriguingly, they exhibited extraordinary order and luminosity, characteristics typically associated with galaxies evolving in the universe's early stages. Ordinarily, galaxies require billions of years to develop. When scientists trace back the developmental timeline of these seemingly advanced galaxies, they appear to precede the universe's age. While some speculations entertain the notion of these galaxies as turbo-developers, such explanations lack serious consideration. The revelations from the James Webb Telescope suggest a different narrative that challenges the established belief in the universe's age or even questions the very existence of the Big Bang. Presenting his solution, Rendra Gupta has stirred enthusiasm among scientists since the summer of 2022. The prospect of a new worldview challenges rooted theories that many researchers have clung to, prompting a re-evaluation of established beliefs. As scientists grapple with the potential disruption of their current understanding, sleepless nights may become more common. Regrettably, not all astronomers and cosmologists are ready to embrace these discoveries as transformative, yet some still cling to older explanations, resisting the call for innovation. In the wake of James Webb's observations, Rajendra Gupta stood apart from those dismissing the possibilities as impossible. He swiftly offered a plausible explanation. Gupta drew inspiration from a theory formulated by Swiss scientist Fritz Zwicky in the 1920s. Zwicky's research on the redshift of galaxies led him to conclusions diverging from his contemporaries, like Edwin Hubble and Georges Lemaitre. As light moves through space, its spectrum shifts from white to red over extended distances, causing the oldest galaxies to appear reddish in cosmic images. In contrast, the nearest stars emit a white or blue-white glow. Edwin Hubble discerned more than just the pure distance to us in the redshift, paving the way for new perspectives in astrophysics. Believing he had evidence that these ancient galaxies were not only present but also moving away from us, this observation led to the development of the Hubble constant, describing the rate at which the universe expands. However, despite being a cornerstone of the Big Bang theory, the expansion itself has yet to be conclusively proven, and skepticism persists. Nevertheless, the prevailing notion is that the universe has been continuously expanding since the Big Bang, an idea that Fritz Zwicky interpreted differently. Zwicky was convinced that light loses energy during its extensive journey through interactions with other particles, resulting in a redshift. Importantly, this mechanism doesn't follow an expansion of the universe and is seemingly incompatible with the standard model of cosmology. However, the innovative professor from Ottawa, Rajendra Gupta, offers a solution even in this context. According to Gupta's expertise, tired light theory aligns seamlessly with existing standard models. To substantiate this, he employs another theory originating from 1937, the hypothesis of variable constants proposed by British physicist Paul Dirac. Dirac posits that certain constants employed to describe forces and particle masses are not eternally fixed, rather, they change gradually over time. Combining this notion with Zwicky's hypothesis, Gupta introduces a novel model that addresses some of cosmology's most profound puzzles and mysteries. Gupta's model explains the existence of stars and galaxies that appear older than the universe by extending their formation and evolution time frame. Additionally, it explains why certain galaxies are smaller than anticipated, attributing their reduced mass to energy loss through light. Notably, Gupta's model challenges the cosmological constant, a parameter employed by scientists to calculate the age of the universe. This constant describes the universe's accelerated expansion, a phenomenon attributed to dark energy. Gupta substitutes the cosmological constant with a novel term contingent on variable constants, demonstrating a significant impact on our estimation of the universe's age. According to these computations, an age of 27 billion years appears most probable, with 40 billion years also within the realm of possibility. However, the apparent solution of variable constants introduces new challenges, and scientists aren't celebrating. The reason is straightforward: Dirac's theory of variable constants raises fresh issues. If particle behavior undergoes such dramatic changes over time that it results in computational errors, our ability to comprehend the early universe diminishes significantly. Zwicky's tired light hypothesis on its own falls short of explaining Webb's observations because it lacks the essential expansion component. Therefore, in pair with the tired light theory, Gupta introduces the covariant coupling constant, or the CCC model. According to this model, fundamental constants such as the speed of light, Planck's constant, and the gravitational constant are not fixed over time. Instead, they undergo variations, extending the timeline of the universe's evolution. By combining the CCC model with the tired light hypothesis, Gupta's work introduces a distinctive perspective on the challenges of early galaxy observations. This approach diverges from the CDM model, where a constant lambda explains the accelerating universe. Instead, the CCC model introduces another constant to account for the dynamic evolution of fundamental constants over cosmic time. Further scrutiny is needed to evaluate which model aligns best with the observations. Gupta explores various possibilities, including the tired light model in isolation, the combination of tired light with the CCC model, the combination of tired light with the CDM model, the CDM model by itself, and an alternative iteration of the tired light model. The combinations of CCC plus TL and CDM plus TL are particularly significant due to a compelling graph. The graph depicts the relationship between the redshift and angular size of galaxies. The blue marks denote galaxies observed at different redshifts before the James Webb Space Telescope, while the red marks represent galaxies observed by Webb. The curves illustrate how the angular size of galaxies varies according to different models. Notably, the currently accepted CDM model, depicted in green, exhibits a turnover at a redshift of approximately 1.5, diverging significantly from the observed galaxies beyond that point. In contrast, the CCC plus TL model, represented by the dark blue line, shows a gradual angular size reduction beyond a redshift greater than 10. This model aligns with observations made by telescopes preceding the James Webb and corresponds with the high redshift JWST galaxies. Aside from comparing theoretical models with observational data, the analysis also involved examining each model's predicted physical sizes of objects. Interestingly, the CCC plus TL model also exhibited an advantage in this regard. According to this model, the sizes of objects at higher redshifts were determined to be 15 to 20 times greater than what the CDM plus TL model predicted. This discrepancy in object size offers a plausible explanation for the observed substantial mass of high redshift galaxies, further reinforcing the credibility of the CCC plus TL model in addressing the challenges posed by early universe observations. According to the CCC plus TL model, the universe would be 5.8 billion years old at a redshift of 10 and 3.5 billion years old at a redshift of 20. This expanded time frame presents more opportunities for galaxies to form and evolve into substantial luminous structures, offering a more compelling rationale for the observed characteristics of high redshift galaxies. Among all the basic and hybrid models examined in the study, the CCC plus TL model possesses superior explanatory power. The amalgam of the tired light hypothesis and the covariant coupling constant concept in this model has resulted in a more precise alignment with the observed data. If the universe adheres to the CCC plus TL model, its estimated age would be around 26.7 billion years. This challenges previous calculations and hints at the potential for a reassessment of our comprehension of the universe's timeline. However, further scrutiny and exploration are imperative to solidify these findings. Presently, scientists are already grappling with challenges in comprehending and describing the behavior of particles. Introducing the element of time-induced changes means that telling how old the universe is nearly impossible, or in mathematical terms, highly elusive. Here we encounter a fascinating point invoking one of ancient times' most renowned scientists, Hermes Trismegistus. In the 2nd century BC, Hermes Trismegistus articulated the nature of the universe through a collection of verses known as Hermetica star. In this summary, the polymath explains the geometry and blueprint of the cosmos with formulas such as above, so below, and that which is within is like that which is without. What is in the large is also to be found in the small. Within the domain of quantum and particle physics research, there is a boundary that Hermes Trismegistus hinted at centuries ago. As researchers explore the infinitesimal realms, deconstructing atoms into progressively smaller constituents like electrons, neutrons, and protons, they come across particles like quarks. Although certain particles can be understood and measured, they eventually reach a critical point commonly termed fuzziness by German physicist Werner Heisenberg. Beyond this point, the behavior of particles becomes so unpredictable that precise measurement becomes elusive. The particles elude measurement at this level, and their description becomes challenging. Similarly, a transformation occurs above a particular threshold in large-scale phenomena along the temporal continuum. The behavior of particles undergoes a shift, rendering them challenging to detect or describe from our perspective. If this holds, we have now encountered cosmic fuzziness, aligning remarkably with Hermes Trismegistus' ancient prophecy, as in the small, so in the large. Thousands of years later, this revelation prompts intriguing considerations about the future of astrophysics. Does this signify the conclusion of astrophysics? Certainly not. Human curiosity and technological advancements will likely propel us deeper into the cosmos of the smallest particles. It will foster the development of new methods to surmount the fuzziness threshold. Throughout history, scientists have consistently embraced new dimensions and ideas, refining their techniques to delve deeper into the intricacies of our world and the cosmos. The current challenges facing astronomy and cosmology are, therefore, not unprecedented. Despite our access to awe-inspiring images capturing more than 93 billion light-years of the universe and our ability to decipher numerous celestial phenomena, the cosmos remains a vast realm with material for millennia of research. Solving the enigmas surrounding the universe's origin has been a persistent human pursuit. The quest to understand the universe's inception holds the promise of shedding light on the profound questions of our existence and its meaning. Should it be verified that our universe follows an unending cycle of birth, growth, and decay, these principles may transcend the boundaries of cosmology, influencing various aspects of our existence. Millennia in the past, ancient cultures such as the Vedic civilization articulated the concept of a multiverse and the cyclic pattern of our being, that is, birth, life, death, and rebirth, portraying us as immortal entities. The certainty of Gupta's findings in his paper remains unknown at present. What we do understand, however, is that his work challenges many currently accepted models of the universe, necessitating a reconsideration of established frameworks. This presents a significant hurdle. The scientific process, adept at observation, testing, and verification, will now scrutinize Gupta's proposal. Determining the accuracy of his research is a task that lies ahead and may take some time. Do you believe these measurements of ancient stars and galaxies need to be revised or revisited? Or does Gupta's work suggest a potential re-evaluation of our fundamental understanding of the universe's age? Is the universe genuinely 27 billion years old, or is this an instance of a physicist delving into the mysteries of the cosmos and getting too carried away? Thanks for watching another episode of Voyager. While you're still here, make sure to click the video on your screen for more mind-blowing videos like this one.